Hello, and welcome to C++ 11 tutorials. I'm your host James, and I'm here to shed a little bit of light on the subject of C++ 11. And today I'm going to be talking about range-based for loops, which is one of the simpler features to talk about. So I figured this would be a good place to start. Let's just dive right into this. I thought I would try and give a little bit of historical perspective on this and show how code has evolved over the years. So let's start with C for a sec. You probably won't hear me say that too often, but here it is appropriate. In C, there weren't really any data structures in the language. If you look at the C standard library, there's really nothing. If you want a linked list or a dynamic array or something like that, you've got to make it yourself. But there is one data structure you can use, and that is the fixed size array. So I can say int r to get an int array, and I can even use this cool curly bracket syntax to initialize the array. I can have this is a pretty innocent looking array. So the exact contents are not important for the purposes of here, but I just wanted to kind of show how you would iterate over an array in C, because doing this kind of thing, it's not new, right? It's not like C++ users have not had a way to do this. It's just the new stuff is cleaner, as I hope you'll see, maybe. Okay, so if you ask a programmer to iterate over this, the first thing they'll probably give you something like int I is 0, I is less than, you probably want to say size of r divided by size of int to keep that portable. I guess you could just stick 5 there, but that's sort of a bit. Now, you might wonder whether this is correct. I'm wondering that now, but we'll see. Plus plus I. This kind of thing is a little bit contentious, especially since if you pass arrays into functions, they decay immediately into pointers, so this kind of thing is just going to be bogus inside a function. But because we're outside a function, we've got an array name. I can say size of r here. And then to print it out, I would, well, this is a C++ thing using cout, but let's just keep this simple. Cout, and then you say r of I, ender. This kind of code is so common that I don't even feel like I need to talk about it. What I am interested in though is if this size of stuff actually is correct. When I was practicing this, I got it totally wrong. Now you probably can't see this. I wonder if I can make the text a bit bigger. No, I don't know how to do that. But you can see 11, 22, 33, 44, 55. Cool. It's just what we expected. But there is another way to iterate through these. So this is like the kind of index approach, where you have an index that you're incrementing. But instead you can have a pointer that you increment. Let me show you how that would look. So you'd say int star of p equals r. So you want to say address of r of 0. Okay, what this line says is make p point to the first element of r. Now you have to be a bit careful because this line is only valid if r is not empty, but you can see it isn't empty, so we're okay. Then you'd say the stop condition would be, or the continuing condition rather, p is not equal to, you'd want to say address r of 0 plus 5, or you'd actually want to say size of r divided by size of int. Like that, plus plus p. And then here, instead of r of I, you say dref p. Now this probably looks a little intimidating if you haven't seen anything like this before, but it's quite simple really. This p it starts off pointing to the first element, and then every time we go round, we increment p. So we fall in, we say, okay, is p equal to this thing? And you see the answer is no, because this points to one past the end. That's what this is saying. this expression is basically just 5. So let me just stick 5 there for now, just to make things a bit clearer. So I take the address, that's the address of this expression, r of 0, the first element. So that's a pointer, that's an address. And then I add 5 to it. So I go 1, 2, 3, 4, 5. I'm 1 past the end. That's what this expression is. And then I ask, is p equal to this? And we see the answer is no, because p starts here, and we're saying, is it equal to here? Those are distinct addresses, so the answer is no. We fall in, we execute this line, so we print 11. Then we increment p, points here, we print 22. Points here, we print 23, or 33 rather, 44, 55, and then it points past the end. This expression is now false, because p is equal to this address, and we break out of the loop. And I can prove to you that this works. Maybe you can't see this, but yeah, get 11, 22, 33, 44, 55. Awesome. So this syntax is interesting for sure, and when the STL was made, it was actually copied for the standard containers. If we include the vector header here, hash include vector, so now we can start using vector. So here I can say instead of int array, this syntax, I'd say vector of int v. And I'm going to use an initializer list, but essentially it's the same as the array syntax from above. I might do a future episode on initializer lists, but all you need to know here is that this is a vector and it has this contents. And a vector is like a dynamic array, and it can get reallocated and whatnot. It's very, very cool. So when the standard library was made, this syntax was actually copied, or the STL had the idea of iterators, which are essentially modeled off pointers. So in here I would say for, instead of int star, which is the type of p here, I would need to say the iterator type, which is vector of int, colon, colon, iterator, I. And that's equal to, that needs to be the starting element of v, and to do that I say v.begin. Okay, now for the condition, here I say p is not equal to 1 past the end. In iterator parlance, you would say I is not equal to v.end. And v.end gives you an iterator to 1 past the end. It's an iterator to this invisible element here. You're not allowed to dereference end iterators, but you can compare them to other iterators, so this is totally valid. And then here I'd say plus plus I. Cool. And then in here I can deal with I just like I dealt with p before. And if we run this, we should see that it behaves exactly the same way. We get -1, 42, 123, 9000. And this works exactly like this, except instead of pointers, we have iterators. And the cool thing about iterators is they're kind of agnostic to the container that you're using. They provide this interface. So it doesn't matter. I could replace vector with list, or deck, or forward list, map, set, whatever. It doesn't really matter. I can still use the iterators in the same way. The only difference being that some containers' iterators are more restrictive than others. So for example, if I have a forward list, that's a singularly linked list, I can only iterate forwards. I can't iterate backwards from a singularly linked list because there's no back pointer. Whereas if I have a std list, which is doubly linked, I can go backwards. And in the case of vector and deck, I have random access, so I can actually offset I with an index, much like I do here with R. Or I could do that with P as well. Which is cool. So, this, I would argue that there's a certain elegance to this syntax in how you treat an iterator just like you would treat a pointer. But the issue is that this is, it's pretty ugly. Let's be honest. It's not pretty. It's quite long. It's a lot of characters. There's a lot of noise here. Like, what I'm actually trying to do in this for loop is incredibly simple. All I'm doing is I am iterating through the container. I'm just taking the elements one at a time and doing something with them inside this body. That operation is so simple, and yet the syntax to do it is so complex, and that violates one of the principles of C++, which is that simple things should be simple. So C++11 comes along, and because all the cool kids are doing it, you can now write range-based for loops. So I would say for, and then I can say int x in v. And here I just talk about x, which is an int, so I don't need to dereference it. I just print it out directly, like that. I'm going to delete some of this white space because it's getting a little bit... There we go. Yeah, so here I don't need to dereference x because it's not a pointer, it's an int. So I just talk about it directly. You can see that this syntax is much smaller than this. It's a lot cleaner, and it's a lot clearer as well. The thing about these loops is that there's nothing stopping me doing weird things inside this body. In fact, that might be the intent of the programmer. Maybe inside this loop I want to delete elements as I go along, in which case I have to be very careful that I don't invalidate my iterators, which is a real problem, by the way, and you should be careful. And if you want better iterator guarantees, you can use a different container like list, but in general, you want to be careful when you do that. And the same goes for here as well. Whereas in here, this range-based for loop, you're actually not allowed to make modifications to the container in here. That's undefined behavior. So you can't do that. If you want to do weird things, stick with the old way, but if you want to do the most simple thing ever, do it with this nice simple syntax. Okay. So that's the range-based for loop. And sometimes people get scared by these new syntaxes. They say, ooh, that syntax is scary. I wonder if there's a runtime cost. It's a valid concern. The answer is there's no runtime cost. Usually. I'm going to have to talk a little bit about this because the first thing you might notice, if you're an experienced C++ programmer, you look at int x and you realize that is a value. Right? That's not a reference, it's not a pointer, it's a value. And I can modify x in here if I want. I can actually say, x times equals 2, so I can double it. But this won't actually change the container's contents. I can show you. You'll probably only be able to see this if you're on full screen. So this loop is run. If I peek at v, the vector in the debugger, none of its elements have changed. They haven't doubled at all. And that's because in this loop, I'm copying my elements, because I just said int here. That isn't really a problem if we're dealing with ints. Ints are pretty cheap to copy. But if I pull in string for a second, and instead of vector of int, I have a vector of string, strings, and I have some arbitrary strings here. If I say, instead of this, if I have string s in strings, this line is probably going to make no sense. That should say s. Maybe instead I'll say string s plus equals 2. So producing the sequel of all these meats, I guess. Again, I'm modifying the string here, but I'm modifying my copy. I'm not actually modifying the inner container. That may or may not be what you want. In general, when you use these range-based for loops, you probably didn't want to capture anything by value. So you can avoid this by sticking a ref here. Also, in the case of string can be pretty expensive to copy. These small strings are probably going to be optimized, but if you have a long string, like something like that, now we're in trouble because this thing probably needs to go on the heap, and this copy here is going to incur you heap allocations and deallocations that you can do without. If you stick a reference here, that saves your copy. Now this loop isn't copying anything. But you notice this is a full-blown reference. I can still make modifications. If it's not your intent to modify it, you can stick a const here. So here I'm saying const string ref s in strings. And then this is complaining. IntelliSense says error, no operator plus equals matches these operands. And that's because I've got a const string ref and I'm trying to modify it, which is illegal. As a little side note, you could still do this the old way if you're stuck in the old ways. In C, you can stick a const here, and this gives you a const int star, which is a pointer to constant int. So via P, you can't modify the underlying int. And if I said star P times equals 2, this is going to be an error. Error expression must be a modifiable L value. And I can get the same effect in C++98 by saying const iterator here. If I say vector int : const iterator, then I is now a const iterator. And if I try and modify the container through I get an error. Just like I would here. And in a range-based for loop, you can do it by saying const type ref. Take out all of that. Or maybe we'll leave the const here. So that's nice. One final little tip that I would give is that instead of uttering the type here, you can stick auto here. This is another feature of C++ 11 is auto. Well, if you're a C program, I'd be thinking, auto? That's not new. That's been here for ages. But actually, it means something totally different in C++ 11. Auto means, please deduce the type for me. There's nothing, again, like, it's easy to get scared by new syntax, but auto doesn't incur a runtime cost either. It's just deducing the type at compile time. And here it's going to deduce s to be string. Or IntelliSense gives me some horrible type def that is a string. In any case, this is what you want for const auto ref elem in elements. If you don't want to modify it, that's what you want. If you did, you can delete the const here, and now you can modify it. So those are the two syntaxes I would recommend. In fact, sometimes if you try to utter the type instead of using auto, you can still get a copy. The example I've seen is with map. If we pull in map for a second, if I've got a map from int to string, maybe this is like a phone book or something. I'm not sure if you can use an initializer list. Give it a go. So maybe I've got 1 is James, 2 is Catherine. This is probably not going to work, is it? Is it? I don't know. Apparently that you can use an initializer list. 3 is Johnny, something like that. I don't know. 3 random names. I think maybe I need to use make pair here. Or maybe I need to convert these to... Oh, no, okay. So that works. Cool. Alright, so there's our map. It maps 1 to James, 2 to Catherine, 3 to Johnny. Here, if I can use map in a range-based for loop as well. If I don't use auto, I'm going to try and be clever, right? I know that the inner type is... It's going to be pair of int and string. So I can say const pair int string ref p in phone book. Okay, and then I can print this out. Actually, I can say cout colon p dot first p dot second and l, like that. And this works, but there's actually so it totally works. I get 1 James, 2 Catherine, 3 Johnny. But there's a copy going on behind the scenes here. And that's surprising because I said const reference. So why is there a copy even though I've said const reference? And that's because this type, I tried my best to come up with the right type. But this is the wrong type. This isn't correct. The actual type is pair of const int to string. And pair of int to string is very similar to pair of const int to string. However, they're not the same. So the compiler has to do a conversion, and in doing the conversion, you get a copy. So even though you thought you were copying stuff, you're actually not. And what's even worse is if I didn't have the const here and I tried to make a modification, that modification is not going through. Also, this is squiggling. Oh yeah, so if I actually... If I don't put const here, I actually get an error. But yeah, you get a copy. And this could be bad for various reasons, mainly because you're making copies, but there are other ways this can blow up. But if you use auto here, you're totally fine. Auto always just means give me exactly the type. Don't ever give me a conversion. And in this case, it's exactly what you want. You don't want a conversion, you just want to peek at the elements. So that's what you should do. And I can run this, and you get the same results. So that's auto. That's range-based for loops, and another feature, auto. I might do another section on auto, but sometimes C++11 is quite interconnected, so it makes sense to bring these up. So as a user of range-based for loops, you should favor either you want to say this syntax for const auto element elements. Sorry, for const auto ref element elements. Remember, make sure you get that right, the ref stuff. If you want to modify it, just omit the const, and you'll get what you want. Cool. Actually, more syntaxes are coming. Apparently in C++17, you can just delete all of this. That totally won't work right now. But okay. So that's that. That's how you use range-based for loops, and a bit of history as well. Now, I wanted to talk one last little thing about the implementation. Let me just get that back. How does this work? And why is there no runtime cost here? How is it that the compiler knows that if I've got a vector, I can use a range-based for loop? And the answer is surprising, perhaps. Maybe not that surprising. Behind the scenes, the compiler is turning your range-based for loops into C++98 style loops. See these horrible loops? This is just syntactic sugar for one of these. And in order for the compiler to do it, it looks for these begin and end member functions. Okay? So, in order to add functionality to your own types, you just need to add begin and end member functions. So I've got a little example here. I've written a little class called myVector. The text is a bit smaller on this. Let me just make it bigger. So myVector is a custom vector that I've just tapped out. It's really the implementation is not amazing. It's just there for demonstrative purposes. Really, this should be declared out of line and stuff. But anyway, here we've got a constructor, and I give it an int, and then this will go and allocate I ints, initialized as 0, 1, up to I minus 1, as it says. I've even written the end here, but forget about that. I've got a destructor that deletes my elements, because I'm a good person. Got a operator square brackets, and I've got a get size so I can query the size. And that's this entire vector, and I can use it in here. So delete some of these includes. All I have to do is include my vector.h, like that. And now I can start using it in my code. So I can say my vector v, and then construct it with, let's say, 10. So v is going to be the elements 0, 1, 2, up to 9. And I can print this out using an index style loop. Int I is 0, I is less than v.getSize, plus plus I. And then here I say cout v square brackets I. Behind the scenes, so I need the end L here as well. Behind the scenes, this is invoking the overloaded operator square brackets here, and all that's doing is it's got internally we've got this int star which points to a load of ints on the heap, and the operator square brackets will just index into that array and pull out the answer. And if we run this, you see 0, 1, 2 up to 9. Perfect. Now this is all well and good, but maybe I want to use a range-based for loop because, you know, I'm cool, I'm hip, perhaps. So instead of this, I'd want to say for const auto ref x in v, and then here instead of v of I say x. But this doesn't work, right? The compiler can't do magic here. It doesn't know what I'm talking about. And IntelliSense here, which you probably can't read, error, this range-based for statement requires a suitable begin function, and none was found. I don't know, there's some kind of elegance about the error. It kind of reads nicely, doesn't it? Yeah, so basically, the compiler looks for begin and end functions, and here it doesn't find any, and so it complains. So, as the implementer, you can fix this in a couple of ways. Perhaps the most obvious thing is you can copy the standard library and add begin and end member functions. So this is what that would look like. I'd say int star begin, and then I want to return an iterator to the beginning. And in this case, a pointer, an int star, is a perfectly valid iterator. And I can say, I just want to say return elements here. So I just take this pointer to the array, and that's a perfectly valid begin iterator. Okay? For end, I do the same kind of thing, except here instead I say return elements plus size. And there we go. This now is not squiggling. If I hit play here, I would like to build. I get exactly the same, 0 through to 9. Beautiful. So all you have to do, if you've got these classes, is provide begin and end member functions. There is an alternative. You can actually provide non-member begin and end. And you might say, well, why would I want to do that? And the main reason is because there are arguments being made that member functions should be minimized. You should try and have some kind of minimum public interface, and then do as much as you can as non-member functions to promote encapsulation and reuse and stuff. So maybe I want to do non-member functions because some guy on the internet told me it was a good idea. So instead I would say here int star begin of my vector ref v, like that, and then in here I just say return. Now you need to be a little bit careful. Before I was a bit careless, I just said return elements. I'm going to say that here as well, but you might notice that elements is private, but I can actually get at it using this operator square brackets. So I just say address of v of 0. This is fine. One problem with it though is that if v is empty, calling v square bracket 0 is going to be an error. So instead I can actually say, I can ask if v is empty. I can say v.getSize not equal to 0, question mark. And if it is, if that's true, so it's not empty, I do this. Otherwise, I return a null pointer. Like that. And I can do end in exactly the same way. Return v.getSize not 0, question mark. Then here I want address of v of 0 plus v.getSize. Otherwise, null pointer. And there you go. This compiles, and it works. Even though I use non-member begin and end. And that's nice. The cool thing about non-member begin and end is that if I'm not the class author, if I don't have access to the guts of this class, I can still add my own non-member begin and end functions. And what's even cooler is that the standard library thought, well, non-member begin and end is cool. Why don't we add those to C arrays? So if you include, I think it's in utility. Don't hold me to that though, but we'll pull in utility. Now, bringing this back full circle, imagine I've got some, smelly old C array, the same one we had earlier. For some reason, I'm working with this array. By the way, if you really do want to work with fixed size arrays, I would recommend that you look up Std Array. That's a C++11 container, and it's fixed size. So it's a lot like a built-in array, but without the problems. Anyway, let's say I've got a built-in array. I can still say for const autoref x in R, and then print out x. And this is working because the standard library has provided non-member begin and end for arrays. They're templated member functions. And at compile time, the compiler is turning this into, it will be auto I is begin of R. I does not equal end of R plus I. Then here I say deref I. And that's how this is working. It's using these non-member begin and end functions on arrays. So I would recommend that you, if you're a class author, define your own non-member begin and end. And also, if you're a user and you want to use these cool range-based for loops, this is the syntax you should be using. You want const autoref elem in elems, unless you want to modify it, in which case omit the const, just say autoref elem in elems. Sweet, so that has been the C++11 tutorial for range-based for loops. Let me know what you think. If you liked it, let me know. You can comment on this video, or just, I don't know, shout at your monitor, I guess. Maybe I'll hear it if you shout loud enough. I don't know. Just let me know what you thought, and if you thought this was too slow, or too fast, or too boring. Yeah, and if you want, more importantly, if you want more of these, definitely let me know, and let me know what subjects you'd like covered next, and I'll see you later.